So in the last lecture, we saw how the Rayleigh-Jeans formula gave a divergent result to the blackbody spectrum. So let us ask why, physically, does that happen? The simple reason is that in the blackbody, when in the box, we can actually accommodate as high a frequency as we like. And therefore, if we associate with each frequency, the factor kBt, then the amount of energy that we're going to have is going to be infinite, because there are an infinite number of modes that can be accommodated within our cavity. So the way out of this was discovered by Planck. And Planck, what he thought is that since the divergence in the energy comes from the higher frequencies, what if there was a way in which it could be made possible so that it's harder to reach those higher frequencies? So what Planck realizes that if instead of thinking of the energy distribution of every mode being a continuum, if he thought of them as discrete, then that would solve the problem. So what he decided was that instead of E being a continuous variable, he said that what if I take E to be an integer times some constant times the frequency, where n is some positive integer. So it's so this is the famous Planck quantum hypothesis. And it's quantum because the energy levels take discrete values, so it's quantized. So how does this help us? So let's go back to the equipartition theorem, or its derivation. So let's rewrite our energy to be E equal to n times some small constant called epsilon. So n is an integer, so n takes the value 0, 1, 2, 3, ... infinity. Then our, the original, expectation value of the energy now becomes a discrete sum. So now it becomes a sum, the numerator. And remember that we had, so the energy here, so the energy E, now the energy E will be n times E. And then we have the Boltzmann factor, and in the Boltzmann factor, instead of the energy, we have n times small epsilon divided by kb of t. And we divide this by the sum of all the probabilities, which is now not an integral, but a sum. So we have e to the power minus ne by kbt. So we can rewrite this in terms of a variable which we define to be x. So x is e to the power minus epsilon by kbt. Then our sum, this quantity, then becomes our summation, which goes from n equals to, the summation which goes from 0 to infinity, and we have n times e, and then we have x to the power n, and in the denominator we also have the sum from n to infinity, and we have x to the power n. So how do we do these sums? So let's look at the numerator, or actually let's look at the denominator first. So the denominator is going to be something like 1 plus x squared, and this is an infinite series, which we know what the result is going to be. It's going to give us this, right? And the numerator is going to be so we can actually factor out e and power of x. Then the sum in the numerator becomes n times x to the power n minus 1. And this thing is nothing but 1 plus, so the first term is 0, and so n equals to 1 is going to be 1, and then we are going to have the next term 2x plus 3x squared dot dot dot. And you can see that you can derive this, this sum, the left hand side can be derived from this guy, but just by taking a derivative with respect to x. So we can actually use this result, and the result of this sum is 1 minus x whole squared. So then the expectation value of the energy we get is, we had factored out epsilon and x before, and the sum from the, x before, and the sum from the numerator gave us 1 minus x, 1 over 1 minus x squared, and the sum from the denominator gave us 1 minus x. So we see that we have a cancellation, and then if we rewrite this, we now express x in terms of e to the power minus epsilon over kt, and if you do this and with one line of algebra, we can write this as e to the power epsilon divided by kt minus 1. Okay, so this is the result. So it's very different from the classical statistical mechanical result, which was kt. For high temperature, when T goes to infinity or very low values of E, this or epsilon, this thing becomes, goes to the, sorry, let me put a B here, the classical statistical mechanical result. But for general temperature, this is a very different result.